Welcome everybody for this week's Tau seminar, and it's with greatest pleasure to have Nicole Riemer here from the Department of Atmospheric Sciences, University of Illinois at Urbana-Champaign. And as maybe some of you already heard in our chat before, Nicole is a former colleague of us, and so many of you know her. But besides that, I give a proper introduction because there are, of course, students and new faculty who were not aware or don't know that Nicole was a faculty member here. So a brief outline. Nicole did her master's at the University of Karlsruhe and her PhD in meteorology as well. And interesting what I found out that during our grad studies, we shared a poster over 20 years ago, side by side. But we didn't talk much at that time or didn't know each other because our research was very different. But we were standing side by side over 20 years ago as grad students. She got a prestigious National Academic Foundation scholarship. This is remarkable, to go to Caltech, work with John Seinfeld for a year as a grad student because education is free in Germany. So there are hardly any fellowships for university studies. Then she did postdoctoral scholar stints at the University of California, Davis, Department of Mechanical and Aeronautical Engineering. Then also another stint at Stanford University and NASA Ames before becoming a faculty here at Stony Brook in our department, in our school, Atmospheric Science Division. And then she moved on to Illinois at Urbana-Champaign, where she is by now a full professor. Just several awards and services she's doing, but I want to highlight two very recent, very important ones. Just a few months ago, she was awarded the HEU Ascent Award for mid-career scientists. That's a nice recognition with some prestigious people in the list there. And since this year, she is editor at Journal of Geophysical Research. Yeah, that is really a big accomplishment. We are glad you're having there and doing this service. So with no further comments anymore, I welcome Nicole, and please go ahead. The title of her seminar today is Particle Resource Modeling, a Bridge Between Scales and Aerosol Sciences.
Thank you, Daniel. This was a very, very nice introduction, and thank you for having me today. It's nice to see you all and to meet the new colleagues and the new students at the department. Yeah, and so I would like to acknowledge my co-authors on this talk to start out with. So it's Joseph Ching, Jeff Curtis, Jessica Gasparik, who is also in the audience, Yu Yao, Zhonghua Zheng, and Matthew West. Okay. And so Daniel told me many of you actually are not familiar with aerosol science, but I'm supposed to talk about particles a lot. So I will do this in the coming 40 minutes or so. Okay. So just as a starter, if you think about recent newspaper articles and you watch out for it, aerosols actually are making headlines left and right and center. So for example, we had these severe wildfires in different states. So this shows an example of California a couple of years back, but it's happening every year again now. So this is a satellite photo, and you see the smoke from the fires accumulating in the San Joaquin Valley. And of course, what's keeping us busy, for the last 2 years, I don't need to mention much more here. The coronavirus also is transmitted by aerosols. And so I think it's fair to say aerosols affect our lives in many ways. And so there are the health impacts on the one side. So the coronavirus is one example, but also all air quality issues. There are many people who die each year as a result of poor air quality. And then there are also the climate impacts of aerosols, and my work focuses mainly on the latter. And so you probably remember from your introductory classes that aerosols scatter and absorb solar radiation directly. And so this is a picture here from India where we see pollution outflowing from the Ganges Valley over the ocean. And then there are also these really important interactions of aerosols with clouds. And so you also might remember, so each cloud droplet forms on an aerosol particle. And due to our activities, by modifying the aerosol population that is out there in the atmosphere, we are changing clouds, right? And so polluted clouds are more reflective because you are supplying more nuclei where the water vapor can condense on. And having more droplets, but smaller droplets, make the cloud more reflective compared to the clean case. And let me just quickly go back. Yeah, if you look at this picture right here, so this is the coast of California, and this is the Pacific Ocean, and there are a lot of marine stratocumulus clouds forming over this part of the ocean. These streaks that you see here, these are ships going underneath the cloud deck, and so they are supplying aerosols where cloud droplets can form on. So we have exactly this effect here in action. Okay, and so if we summarize climate impacts, this iconic slide from the IPCC report, that's from the last one. The new one still has the writing all over it, don't distribute. It's still in draft mode, so I didn't put it in here, but it looks very similar. So on the x-axis here, we have the radiative forcing. Everything that is going to the right and is highlighted in red means it's exerting a warming impact. So we have CO2 here, of course, and then other greenhouse gases. And then there are the aerosols and the aerosol radiation interaction and the aerosol cloud interactions here at the bottom. And they are offsetting the warming due to CO2, right? So this goes into the negative and it's highlighted in blue. But what we always look at here and what I would like to draw your attention to is these huge ranges. And so sometimes people refer to these as error bars, but really what this is, it's the range of model outputs, right? So the models that go into this analysis, which are many, they don't agree. And so there's a whole range of results that they get what the radiative forcing of aerosols is due to aerosol radiation interactions and aerosol cloud interactions. And that's somewhat surprising because we have gained so much knowledge about aerosol formation, aerosol processes in the atmosphere, what's going on the particle levels. Why has this been such a struggle that we are still having this big model spread? So why is this so hard? And I'm trying to explain why this is so hard with this slide. Really trying to make this point, it's a multi-scale problem, right? So we have all these processes going on the molecular scale even, and on the particle scale. And we may actually quite well understand what's going on there, but then we have this challenge to put these processes into a global model. And anyone, if you had any interactions with global models already, you know that you have to simplify, right? So there's a lot of processes that you need to represent. Aerosols is just one of them. So we have to parameterize what's going on the particle level. And sometimes this is really hard to do, right? So we are using ad hoc empirical parameterizations, trying to do our best to capture what's going on. But it's really hard to do this from first principles. And so then you can imagine it's no wonder that different models get different results because they use different representations. Okay, so aerosol science as a multi-scale problem. And that's not unique to aerosol science. Other areas in science have similar problems. Okay, and so talking a little bit more about the processes that are going on as aerosols are going through their life cycle in the atmosphere. So trying to highlight this in this sketch. So you might have an industrialized area here. And so your background air is coming with a certain aerosol population that has a certain composition, right? And so as this aerosol is transported over this area where we have lots of different emissions, that aerosol population is modified. And so there are a few key processes that are going on. So the first one is that we might have direct aerosol emissions from all kinds of different sources, right? Industry, traffic is a big source, agriculture. And so then these aerosols are mingling with the other ones that come from our background transported into this area. And then there are other processes that involve the gas phase. So along with aerosol emissions are a whole bunch of gas phase emissions, so SO2, for example, many different volatile organic compounds, nitrogen oxides, ammonia, and these undergo reactions that form products that then can condense on the aerosol. So in addition to primary emissions, we have what we call secondary aerosol formation, so formation of aerosol material from the gas phase. And then the other thing that happens is that particles bump together. We call this coagulation. And then, of course, you're creating a new particle that combines the different species together from the original two particles that collided. That's another thing that can happen. And also indicated with this little cloud here, each cloud droplet is essentially a little chemical reactor, right? So in this little chemical reactors, we also produce aerosol mass, and many clouds actually don't rain, they evaporate, and then they release this modified aerosol population into the air. And so then you might imagine this cloud of aerosols with all this stuff going on is exiting this area of industrialized activity and is advected over the ocean maybe, and then a new type of aerosol is entering the population, right? So sea salt and then different chemical species participate in this cycle, and the transformations are going on, right? And so as the end result, aerosols are really complicated mixtures, and this is important if we want to assess what are their properties or what are their abilities to form cloud droplets, what are their optical properties, and what are their abilities to form ice in the atmosphere. And so now I have a little exercise for you, and so just going back real quick. In this industrialized area, we might have somebody from Brookhaven Lab, for example, doing a measurement like this, and that would be a typical result, right? So this shows a size distribution. So there is diameter on the x-axis, and on the y-axis is how much mass we have at a given size, right? And so you see most particles, maybe here where the maximum is, have a size of about 500 nanometer, but it's a range, right? It's a polydispersed distribution. And the colors tell us something about the composition. And so the green means it's organic aerosol, red means sulfate, the blue is a little hidden here, it's nitrate, and the yellow is ammonium. And so the total, if we add everything up, is the black line. So it's telling us about the sizes, but also about the composition of the aerosol population. And here we see a pie chart, right? Most of the aerosol in this location is organic. It occupies almost half, but then we have the other species as well. All right, so the question for you is, if I take out like a slice here, around the maximum 500 nanometer, and now you in your head, you're translating, you're taking samples, right? Like how many do I have? I think 10. A sample of 10 particles from this population. How would you draw the composition of these particles, knowing this piece of information right here? And I'm hoping now that this poll is working. All right, so let's give this a few moments here until everyone made up their mind. Is it A or B or C? And yeah, C. Steve, it looks like you can't decide. All right, let's give it 10 more seconds.
It could be any of them.
Are you sure?
That's my quick answer.
All right. 3 more seconds. Wow, there's still some people making up their mind. All right, I'm stopping it now. Okay. And poll, share the results. Can you see the results now? Yes. Okay, good. All right, so most of you guessed B, some of you guessed A, and some of you guessed C. So I would say it's not anonymous, right? So, and let's see what I think. And Steve had a good point. So I would say any of these are possible manifestations of what this aerosol population could look like, because you just don't know, right? From this measurement, you don't have the information about on the particle level. We know how the composition changes with respect to size, but not if we pick a certain size, what the composition might look like. So when I first drafted this slide, I made a check mark on each of the three possibilities, because as Steve correctly said, we just don't know, right? But on further thinking, because the blue is nitrate, if you know a little bit about aerosol chemistry, there are no pure nitrate particles, I would say, right? And so I excluded this B case, and I just put this check mark on A and C. But the point of this slide exercise really is to get you thinking about the particle level composition and to highlight this idea. There is this thing we call aerosol mixing state, and that's the distribution of chemical species across the population. It's a property of the entire population, and you can distribute your aerosol species in many different ways. Actually, not just these three ways that I drew here for simplicity. You could make up many, many more mixing states, right? And so, yeah, so that's the whole point of aerosol mixing state. It can vary between what we would call a perfect external mixture. So this was the case B, right? To a perfect internal mixture. This was case A. To something in between, and that something in between is most likely what's actually going to happen in the atmosphere. We rarely see this perfectly external mixture, and we also rarely see a perfectly internal mixture, because there are always these fresh emissions being injected into our populations, and the aging is going on at the same time, right? So there are many reasons why, even if the aerosol starts out one way or another, we might produce these intermediate states. All right, so now everyone knows what is aerosol mixing state, and so why does it matter? So coming back to the things we are actually interested in, right? The climate relevant properties. The number of CCN that I get from an aerosol population can really depend on if I have an external mixture or an internal mixture or anything in between. And so this is highlighted here for an example where we have about half and half ammonium sulfate and a hydrophobic organic, right? And so you could imagine you put these two species in as an external mixture, and a hydrophobic organic doesn't really activate very easily. And so in your cloud, given a certain supersaturation, you just activate half of your particle population. And then you compare this to an internal mixture where all the particles have a little bit of sulfate, and the hydrophobic organic, just this little bit of sulfate really helps, and your whole population might activate. And so in reality, it might be something in between. And so the number of cloud droplets really determines the reflectivity of the cloud, but also the lifetime of the cloud. So it's kind of going down the line, right? So if you get this wrong here at the beginning, you might incur errors in your prediction going further down the line. And similar arguments apply to optical properties and also ice nucleation, right? Okay, so now, having laid out the foundations about aerosol mixing state and why it's important. So how do models deal with this? So it turns out that really representing the diversity of particles is something very challenging. And so in traditional aerosol representations, what we do is we use size as the first order thing that we are interested in, right? And so we use models that are based on distributions. A variant of these models are called modal models, and another variant is called sectional models, or if you come from the cloud community, this would be your bin microphysics model, right? And so since size of particles is so important, so this is a really good approach. But what this means is we pay by losing detail on the composition, right? So within one size or one bin or one mode, we have to make this inherent assumption that all particles have the same composition. And so therefore, this whole idea of mixing state, right, that we can have diversity at a given size range introduces a structural uncertainty of these models. So it's embedded in the structure of these models that we actually don't know anything about what the mixing state looks like. And so one of the questions that we are pursuing in my group is, does this matter? Do we actually need to track all these details about particles, or maybe it doesn't matter, right, for many circumstances or situations? And so to tackle this question, does it matter? We embarked on this adventure developing a new type of aerosol model where we don't constrain our aerosols into bins or modes, but we do this thing over here, right? So we basically resolve the population by a whole bunch of many computational particles. We are sampling the population by many computational particles, and then they can evolve freely in terms of composition and size, right? And so this whole idea about mixing state and having different compositions at a given size is very straightforward to represent. And if you are not familiar with aerosol modeling at all, and I would have asked you, this would have been another good exercise, design an aerosol model. How would you do it? You probably would have come up with something like this, because it's kind of straightforward, right? So in the reality, we have all our aerosol particles. So in the model, we also have these particles. Now it's computational particles. It's in some sense much more straightforward than having these distribution-based approaches. However, the thing that makes it challenging is it's computationally expensive, right? To track each particle separately. Which is why in global models, we still want to rely, or we still want to use simplified representations. But it would be really good to know what is the error that we are committing in CCN concentrations, in optical properties, if we do that. Okay, and so the model is called Polymc Mosaic. And so the two components are, the Polymc is really taking care of the aerosol dynamics, right? So it's doing the coagulation, it's doing dilution and transport processes, nucleation, and it's doing this stochastically. And then Mosaic is actually an aerosol chemistry module that was developed by Raul Zaveri and collaborators at Pacific Northwest National Lab. And Mosaic is used in many other models too, for example, WRF-Chem, right? So some people who might have used this, you are familiar with this. And that Mosaic simulates the gas phase chemistry and also the aerosol gas phase partitioning. So and in WRF-Chem, for example, if you know that it's used to in conjunction with a bin model. And so here we have coupled it to our particle resolved model. And so we calculate the chemistry and the partitioning on each of these computational particles. Okay, and so what we do, this all started out as a box model, and that's what I thought it would be, right? It would be a computationally expensive benchmark box model that we use if we really want to know what's going on the particle scale. But then some years ago, 7 or so, Blue Waters came along, a supercomputer at Illinois, and a very brave graduate student, Jeff Curtis, who embarked on this adventure to implement our Polymc box model into WRF-Chem. So we took out the chem of WRF-Chem and put out our own particle and gas phase mechanism. And so now we have this happening here. So we often simulate California because there was a very detailed field campaign some time ago. And this shows here the number distribution of the aerosols, which is something any aerosol module should give you, right? But we can drill down and pick a certain grid box, and then we know in each of these grid boxes are about 10,000 computational particles that we track. We know the full mixing state. We know where the source, what the sources were of these particles. So that's a very easy thing to remember, right, in these particle-based approaches. And we can go down to the composition of each particle. Okay, and so the role of PodMC in the model hierarchy now is we have a tool to verify these more simple approaches like a modal model or sectional models that are still, they have their place in the model hierarchy if we want to go to the global scale and we want to simulate like long times, right? Where we need something cheap-ish, it's not that cheap actually, but comparatively cheap and efficient, computationally efficient, I should say. And we can also use it for what I call here coarse graining. So with PodMC, we simulate processes in very great detail, and we can use this to, for example, develop parameterizations that then can be used in these more simplified models. Okay. To move a little bit more quickly here, I think. So for the remainder of the talk, I will show you a few applications now, where we use PodMC to learn something about mixing state and how it's distributed in space and time. And to do this, we have to get one more thing out of the way. And so this is a metric for mixing state. So what we found was it would be really good or useful if we could label our populations with a number that quantifies how externally or how internally mixed that population is, right? And so we call this index chi. It's based on diversity metrics that are used in other fields, and it's based on we need the per particle mass fractions, right, to construct this metric. And it's the bottom line is for a perfect external mixture, this mixing state metric is 0, and for a perfect internal mixture, it's 100%. And so the really useful thing is really what happens in between. So where am I on the spectrum between 0 and 100%? And so if we know the mass fraction of our particles here, which we do in our model, at least, we can calculate this mixing state index and assign a number to this state. And so it's based on these diversity metrics right here. So literally for each particle, we know the mass fractions, and then we calculate the diversities like this real quick. And so the way it comes out is if I have species in equal amounts, I'm getting a integer number, so 1, 2, 3. And if I have species in uneven amounts, I get something in between. So you will recognize here, so this is actually like a Shannon entropy here, this HI, and then we take the exponential of this HI to get the diversity and this gives nicer numbers, right? And so then we average this DI for the whole population, and that is my alpha diversity. And then we do the same thing for the bulk, right? Forgetting about particles for a moment, but we know the mass fraction in the bulk, and so we can calculate a diversity for the entire population. And then the mixing state index is essentially the ratio of the two, right? And so if the diversity of the whole, if the average diversity of the particles resembles the bulk completely, then this is what an internal mixture means. And if it's if they just have one species in it, I'm getting a 0 here. And so this comes out as the completely external mixture. Okay. That's the mixing state index. So now we have this metric that we can assign to each population. And so we have used this to do error quantification studies, right? And so we often would plot things like this. So mixing state metric here is on the x-axis, going from externally to internally mixed. And each dot is representative of a population here. And we did this exercise. We know the full mixing state, right? Because we know all the composition of each particles. And then we compare this. What happens if I just average our compositions of this population? If I don't know, if I want to gloss over all these details, and what is the error then that I get in CCN concentration? And so as you can imagine, as I'm moving to a more internally mixed population, the error goes down. Yeah, that's not surprising. But if I'm at more intermediate mixing states or low mixing state indices here, so more external mixtures, the error can be up to, in this case, 140%, right? And so, yeah, so there's this relationship that we can see easily here. Okay, so moving on a little bit more towards connecting to measurements. So just like we have our particle resolved model, to simulate particle level details, there are many instrumentation tools that can measure particle level information. And so Daniel, for example, is an expert in this. And so there are many other colleagues at BNL who work on this. So there's spectral microscopy, for example, or mass spectrometry, or we can look at these particles with electron microscopy. And now if we want to connect the modeling and the observation by using this mixing state metric chi, we really need per particle mass fractions, which is easy to come by in the modeling, but it's actually really challenging from an instrument point of view, from measurement point of view. And so I just wanted to show a couple of applications where people have done this. So one was a study now some years ago in Paris called Megapoli, where Rob Healy measured many particles with a ATOF-MS, like one of these mass spectrometry instruments. And he was calculating this mixing state index for the entire duration of the campaign. And so you can see how it varied between, in here, 40 and 70%. So this highlights again, it's never completely externally and never completely internally mixed, right? It's always in between. And then we have this period, which he called, this is the marine period, where they got clean air from the ocean. And so the site in Paris was dominated by local emissions. And so you get more variability in mixing state and lower values, right? So these are the local emissions that you're seeing and where stuff is more externally mixed. And then in contrast, when they got the air from the continent, which with age pollution, this gave, more like a more internal mixture, even though not completely internally mixed, right? And maybe less variability here, at least in this first part. It looks a bit different in the second part right here. So that was one thing. It varies temporally, and he looked at diurnal cycles in more detail. So that was a really interesting study for us to see. And then a few years later, the group at Carnegie Mellon, they wanted to know how the mixing state index varies spatially. So they drove around Pittsburgh in different neighborhoods and sampled the particle population with an AMS instrument. And then what they found is so this color bar here shows chi. In the downtown area, you get more externally mixed population. Again, this means you have your fresh sources, right? Stuff is not as aged, so you have more higher diversity of particle types versus in the surroundings, especially like upwind, right? So the populations are more internally mixed. And again, it's never 0 or 100%, right? It's always in between this spectrum between externally and internally mixed. And so I was visiting CMU at one point, and they were showing me these results, and the grad student, Qing Yi, who worked on this, he was asking me, so how many particles do you think I should sample? Or how many are enough to really constrain the mixing state index? And I actually didn't know. But I had a very ambitious and talented grad student at the time, Jessica Gasparik, who I mentioned this to, and I said, you know what, this would be a really good side project. Famous, the famous side project that kind of take over. But it was really fun to investigate this. So I'm using her slides here. How many particles to determine mixing state? If this is the true population, right? If you only sample a few, you might get a certain answer. And if you sample more, you might get a different answer, right? But how many do you have to sample to get to the true answer or close enough? And so she carried out a large ensemble of PartMC simulations, right? Where we varied the input parameters to get, really the purpose is to construct many different mixing states, as many as we can. And then she subsampled these populations, and that mimics what the instruments do, right? So she took one population, and we use many, many particles to simulate as our truth, right? Model truth. And then we subsample using 10, and we do this many times. We subsample using 100, we do it many times, and so on. And then we see what we get. And so what we get is something like this. So we have the sampled chi value here on the x-axis, and on the y-axis, the frequency. And so if you only use 10 particles to get your chi value of the population, and you do this many times, you get the blue distribution. So, and the true value is somewhere here, it's 40-something%. So you overestimate, right? And then if you take a little bit more, 100, say, you get closer, but it's still pretty broad. And then finally, if you take 10,000, you finally get, okay, pretty narrow here around the true value. And yeah, so the fact that we overestimate, if we use too few, that surprised us. We thought it would be just spread out really wide and then narrow, narrow, narrow. But there are good mathematical reasons why this has to be. And it's explained in this paper why, because of the functional dependence of the diversity metrics, it will result in an overestimation. All right, I will skip this one in the interest of time. Then the last thing I want to show here is, now that we know something about how chi varies spatially, right, in a small region, like the measurements from Pittsburgh, and temporally, like the Megapoli campaign was a really good example. How does it vary over at least a month, in a winter month in this case? I think this came up in one of the ASR meetings, like how could we construct like a global map of mixing state, right? So clearly global models, they have, with their aerosol representations, they have some notion of mixing state, but not the full representation, right? And so with our particle resolved model that I introduced here briefly on the regional scale, yeah, we can simulate 2 days, right? Using like thousands of cores on blue waters, burning a lot of computation time. So we can get to a mixing state metric, and we can construct these maps for our little small episodes that cost a lot of computational time to simulate, right? So here's an example what this might look like comparing to a morning and an afternoon time. But really, to do this on the globe, running PartMC on the global scale is just too expensive and too impractical, right? It takes too long, and we cannot do like many years, for example. And so what we tried instead is to train a model of chi to predict mixing state with the things a global model knows. A global model actually knows a lot about aerosol and the chemistry, right? So it has certain outputs depicted on the left here: temperature, ozone, dust, and many others, which I didn't show. So we know that. And so we thought it would be really cool if we could stick these things into a machine learned model that we trained on PartMC data. And then it spits out this mixing state map on the globe. So this is what we want. We want to predict chi for every grid cell based on quantities that a global model, in this case, it's CSM, knows. And so then that's what we did. So we conducted, again, many particle resolved box model simulation and try to simulate like different conditions around the globe, right? So that we cover our mixing states as best as we can. And the model type here is XGBoost, that worked best compared to other things that we tried. And the features that we use is the bulk aerosol concentrations, gas phase concentrations, and some information about meteorology that are all available in CSM. And so then that's how we construct the machine learned model for chi, and that's an example of a result, right? Showing seasonal averaged maps of mixing state index. So again, 100% would be internally mixed, 0 would be externally mixed. Just like in the measurements, we never get really 100% or really 0%. It's always in between, and then in the paper, we explain all the features. So just to highlight one, so the Atlantic Ocean here pops up as fairly externally mixed, although not completely externally mixed, right? And so this is because we have dust and sea salt, these primary emissions separately coexisting, and they are not mixed in one particle. So this is what Part MC tells us, right? What it thinks it should be based on all the other conditions that are present in the global model. Okay, and we have, to put it mildly, some validation challenges because there are very few chi measurements out there. So I highlighted these two from Paris and from Pittsburgh. And qualitatively, you know, order of magnitude, if you take into account the season when they did the measurements, it's not contradicting what we simulate, but this is far from a rigorous validation. And so I'm lobbying for our particle-based measurement people to tell me, can you construct chi, right, from your measurements? It's not easy to do. You need many auxiliary measurements at the same point to actually do this. But it would be really cool to know from the measurement perspective, what is the mixing state, right? If we look at the globe. Okay, last thing I wanted to show, coming back to this structural uncertainty. I mentioned the global model and MEM. This is like a type of modal model that they use in several global models. It's called MEM4 because it has 4 modes. The global model knows something about mixing state, right? It knows, for example, is the carbon aerosol separate from the rest, or is it mixed with the rest, right? So they really try to simulate black carbon aging. And so they have a separate mode for the carbonaceous aerosol. But there are a lot of assumptions in the placement of these modes and how we shift mass from one mode to the other. So again, a lot of structural uncertainty due to the aerosol representation. And so how big is it, right? So how well does a model like MEM4 represent mixing state? And so now we can do exercises like this, right? So we have our PartMC machine learned output. Again, this is not directly simulating the particles on the globe, right? This is using this machine learning intermediate step that we need to do because it would be too expensive otherwise. And we get a distribution like this, for example. And then if we calculate chi from what the MEM4 output actually tells us, we get this picture here, right? For this is an annual average in this case. Okay, and so you see immediately there are quite lots of differences, right? So MEM4 stuff is more internally mixed in the lower latitudes and quite externally mixed actually in the higher latitudes. So our PartMC manifestation thinks actually the opposite. And so the question, who is right? Again, it would be really cool to have a more rigorous observational foundation to decide, you know, where are the weaknesses here and there, and where do the individual models get it right or wrong. Okay, I think I'm at the summary with this. So I try to highlight the challenges in aerosol modeling that come about because we have this complex system, right? And particle resolved modeling is a key tool in our model hierarchy that we use to assess the structural uncertainty in aerosol models that we have been using for a long time. And machine learning is a key tool to bridge between model at different levels. And with this, I'll put up the code availability and take any questions. Thank you.
Thank you, Nicole, for this great talk outlining the complexity of aerosol particles. That's wonderful, and also challenging us experimentalists. So I see here already questions coming up. You can also type in the chat and then I will read the question. I think Edmund was a second quicker than Paul Shep. So Edmund, please go ahead.
Hi, Nicole. So
Hi,
great to see you.
Hi, it's good to see you.
Yeah, great to see you. Yeah, I have a question, obviously, not on the model itself, but on the implications. Now, you mentioned it sort of obliquely, why we are so interested in aerosols because of the aerosol forcing on climate that we need to model. Now, from what I heard is that CMIP6 models, which try to incorporate more aerosol physics in it, have been at least considered to be too sensitive. Actually, a lot of models actually have pretty high sensitivity, including CSM and the E3SM, with sensitivity nearly of doubling CO2 nearly up to 5 degrees at equilibrium. So what do you think about that? Is that due to aerosol forcing, or maybe actually some people have written about that already? Maybe Menghua or Steve actually might respond to that also.
Yeah, that's a really good question. So I don't know. So Minghua and Steve, you probably are really the better people to answer this question about if somebody has investigated this already. To me, it seems like a thing, you know, when we try to make things more mechanistic and put in more processes, the end result of our predictions not necessarily get better, right? Because there are more things that could go wrong. Rather than using something that is a pretty simple parameterization to start with. Of course, if we stick to the very simple parameterization and we don't have the mechanistic understanding, then we cannot really explore sensitivities, right? And so there is value in putting in more physics and more mechanistic processes into these models, but there is also more room for getting things wrong. And I think it's one of the things that are getting. If Minghua, and Steve, I would be curious to hear your take on this. But if this is what's happening, then I think it has to get worse before it's getting better. And until we really get the mechanistics correct, right? So that's a big challenge. Yeah.
Yeah, so I will let Steve answer.
Yeah, if Steve or Minghua have comments on that directly, we do that before Paul Shepson poses his question.
Yeah, let me take the floor for the moment. In some sense, we don't know what better is, because we don't know truth yet. And early on in the talk, you spoke to what these error bars represent, and in some sense they represent diversity amongst estimates or models, as opposed to being real unknowns, because we don't know what truth is. So when you say things will get worse before they get better, there'll be more model diversity before there is less model diversity. And in some sense, we have to let 100 or 1,000 flowers bloom on this before we can really, in my judgment, before we can really converge on less model diversity, because our understanding gets better. So that would be kind of my answer to the question that got thrown at me. Yeah.
All right, thank you, Steve. So before I let Minghua and Steve pose a question, Paul Shepson, it's your turn.
Thank you. Hi, Nicole. It's great to see you. Welcome back home. Whatever's the right way to say this. Nicole and I have known each other a long time, but not really in any way through our common Stony Brook connection. So anyway, great to have you here. I really enjoyed the talk. I just want to ask a question about the observations of mixing state. So you showed data from various places, Pittsburgh and Paris, but they're surface samples. And what I wonder about is what we know about the vertical profile of mixing state. Like when you get to the top of the boundary layer where the particles might be on average a day or two old or above when they have been processed by and spit out by cloud droplets. So in terms of our observation, what do we know about the aerosol mixing state in the part of the atmosphere where the relative humidity is 100%?
Yes, that's a really good point. Yeah, the studies I showed are surface data. I don't know of any study along those lines who would have probed mixing state in that way higher up, right? So again, that would be a great thing to do. We have looked at cloud processing in our model world, right? Cloud processing of aerosol particles. What does the cloud spit out after it did a while of aqueous phase chemistry? And they do come out more internally mixed. But it only, of course, affects the portion of the aerosol spectrum that form cloud droplets. So there are still a lot of interstitial aerosols potentially, right? And they didn't get modified, so they remain. They basically uphold the degree of external mixture, unless you really activate everything. So that's, we have a paper in JGR actually, where we show this, but that still remains to be proven or disproven by measurements. I think it's difficult to do because it's difficult to figure out what went in the cloud and what got spat out, right? So, yeah.
So just a comment, Carrie Pratt and I are in the Arctic right now doing aircraft sampling. So I'll talk to her about this issue. Yeah.
That would be great. Thank you.
Thank you.
Right, thank you. The next one is Minghua Sang.
Yes, so before I ask my question, I want to follow up with what Edmund asked and Nicole, Steve responded. Both of them said what I agree. Now, the process understanding is the first step for future improvement, but that does not mean like you would improve GCM simulations right away. The problem is there is still a big long gap regarding the activation of cloud particles. So how many aerosol particles would become cloud particles? You really need to know the, say, the fine size distribution and then the composition. The GCM can easily say, assume whatever you increase would become cloud particle that would immediately affect the particle size radiation calculation. So you can imagine that is one of the biggest uncertainties regarding, say, how many aerosol particles would share the liquid water, then that would have a radiative impact affecting the sensitivity to aerosol forcing. So my question to Nicole is regarding the computational amount that you had to deal with. I was really happy to see that you put this in WRF and actually run WRF simulations. So how long did you do the simulation, and what's the amount of computation?
Yeah, so that's this thing here, right? Yeah. So we typically simulate a few days, 3 days, let's say, and then we don't look at the first day. And then the time, we try to use as many processors so that the if we want to simulate 3 days, it gets done below 3 days, right? It's not in the computer for longer than the simulation, the time that we want to simulate. So if we want to do a 3-day run, then we have to wait for about two days and a little bit to get the results.
So a large amount of processors, do you know how many?
Yeah, like this many.
Okay, wow.
Over 6,000 cores, yeah.
For like basically 1 day simulation to get
Mm.
for one war clock
Yeah.
a day.
But it's a little bit faster. We were pleasantly surprised. So I should also say Blue Waters it's down now. It doesn't exist anymore. So we went through like a big scramble at the end of last year to get one more run in, and it was actually a little bit faster than this 1-to-1 day guideline that we try to achieve, which is good. So, but now we have to run it on a different computer. So it's yeah.
Thank you.
Yeah.
Very impressive.
All right, thank you. The next one is Steve Schwartz. Please go ahead.
Yeah, I typed up some questions during the course of the talk. I have 6 sort of independent questions, but Daniel will have to cut me off. My first is just an observation that you speak of unknown unknowns, but I think you're making those unknown unknowns known. So,
right.
so that's already in advance. I got fooled on your quiz because of the looking at the different particles, and you have pure nitrate. I think your unit vectors have to be in some way practical. They can't just be an ion. They have to be something that in fact could exist. Okay. My observation is you showed in Paris this chi as a function of time. You showed in the Pennsylvania area as a function of location. But I think there's another dimension, which is size. So I think chi is going to be very size dependent. And I would ask you whether, in fact, you're looking at that dimension as well.
Mm-hmm. Yeah. So these results, the way the instruments worked, they were all throwing the submicron particles together in one bucket, right? And they were calculating chi for the entire submicron population, not discriminating across size bins amongst those particles. So one thing that happens with chi, the way it's calculated, it weights larger particles or heavier particles more heavily. And so if we throw all the submicron particles together, what this chi really means is it's kind of the bigger particles within that group, right? So the small, we might have many really tiny particles, but they don't factor in that much into the chi value. So it's kind of like an implicit weighting of different particle sizes just based on how the metric is calculated. We haven't really done a calculation where we show a size dependent chi where we bin the particles first, which we could totally do. Yeah, we should do this. And you are completely right. I mean, that will change with size. We sometimes do coarse and fine. I guess it comes because we have these modal models in the back of our mind that we sort of like want to compare to, and they assume within this submicron mode, everything looks the same kind of thing. So yeah, but that's a good idea. We should just bin the particles and calculate a size dependent chi and see what that looks like.
Yeah, I think from an observational perspective, the single particle mass spec might, if you had enough particles, and your side study showed how many particles you got to get. But if the single particle mass spec might be an approach to that. Let me just say a couple of things else about observation, which might or might not be practical, but sort of some thoughts. One, as far as CCN are concerned, we do have a capability of separating out the cloud droplets from the interstitial particles and then looking at them independently. The CVI comes to mind that you could then do single particle mass spec on each of those fractions. That's again, something that's going to require a lot of instruments, start on the ground, and then see if we can get it on an aircraft, get it in fog. People years ago used to look at mountaintop fogs and try to look at composition that way. And that might be a surrogate to address Paul's question about the altitude dependence. Just going back, way back in history, we did aircraft measurements where we were looking at light scattering coefficient of interstitial air when broken clouds. And essentially all the light scattering coefficient, which is your accumulation mode particles, 90%-ish or something like that, got incorporated into the cloud drops. It didn't make it into the measurements when we were looking at the interstitial air. So that's an observational perspective. I don't know how general it is. We were looking in sort of Eastern North America for those kinds of observations. So those are just a couple of observations about the kind of things that might simplify some of these calculations and use observations to train your model more complex models. That would be my perspective on that. Okay, but thanks for a real nice talk. Very nice, very stimulating. Thank you.
Thank you, Steve. These are really
all right. Thank you, Steve. And Jessica Gasparik, a grad student here, former student of Nicole, has the last questions. Please go ahead, Jessica.
Hi, Nicole. It was so nice to hear from you, and that was a really interesting talk. I had a quick question, I think, about slide 23.
Oh my goodness.
Very specific.
Yeah.
Just wondering how these errors were calculated.
Okay, so we basically did like a scenario library, just like you did. And then we have many populations where we know the mixing state, right? And we know exactly what each particle is made of. And then we do this thing that we call composition averaging. So we average the composition of all particles, and we assign the same composition to each particle. And then we calculate CCN concentrations again, right? And then you will get a different result. So the first time you calculated doing your best effort with knowing what each particle is made of. And then the second time you calculated by average the composition of all particles first and not change the sizes, but just the composition, and then recalculate CCN, and then you take the difference. And then on the y-axis is the difference, are these differences, are these errors. And the more externally mixed the population started out, the higher the error gets, right? So that makes sense. But the question really was, how high does it get, right? Is it like 10% or is it 500%? So it turns out it looks like this.
Thank you. That's interesting.
All right. Thank you, Nicole. Of course, I could ask, for 2 hours. I just want to pose you a challenge or maybe a comment, and then we finish this discussion. You talked a lot about the composition of the particles. Did you consider or have you implemented the phase states? And what I'm hinting to is all this amorphous organic aerosol. And the boundary layer where measurements are, it's more humid. They are maybe more like a liquid. They coagulate different. In the free troposphere, they are solid. They bounce around.
Yes, so this whole phase and morphology is kind of like the elephant in the room, right? In my model world, particles look like this. They are spherical, they are pie charts. If we have to calculate optical properties, okay, we might make an assumption that the absorbing thing is in the middle, right? We have a core shell configuration. I would love to look at these viscosity questions and calculate glassy temperatures and or apply this and do it, but we haven't done it yet. This modeling framework lends itself to it though, because it's something that we can easily track and implement, right? As long as we have like a theoretical foundation, what we should use. And yeah, it's just something that we haven't gotten to yet, but it would be a really nice project to do.
All right, so great, thank you. So with that,
sounds like another dimension.
Yes. Mm-hmm. Yep.
Okay, with that, I want to thank Nicole for this wonderful talk. Once again, thank you for being here.